Have you ever gazed up at the moon and wondered how it came to be? This celestial body, our closest neighbor in the vast expanse of space, has been a source of fascination for humanity since time immemorial. From ancient civilizations who worshipped it as a deity, to modern scientists who study its craters and valleys, the moon has always held a special place in our hearts and minds. Today, we're embarking on a fascinating journey into the origins of the moon. It's a tale spun over billions of years, one that involves cosmic collisions, molten rock, and a dance of celestial bodies that continues to this day. How did this silvery orb come to orbit our planet? What processes were involved in its creation? These are the questions we'll be exploring in this video. Over the years, various theories have been proposed to explain the moon's formation. Some suggest it was captured by Earth's gravity, a wandering body reeled in from the depths of space. Others believe the Earth and Moon formed together, twin siblings birthed from the same swirling cloud of cosmic dust and gas. But the most widely accepted theory, the one we'll be delving into, is a bit more dramatic. It's a story of a cataclysmic event that dramatically reshaped our planet and resulted in the creation of our moon. It's known as the giant impact hypothesis, and it's as thrilling as it sounds. As we embark on this journey of discovery, let's keep in mind that our moon is unique. There's no other moon in the solar system quite like it. Its size relative to Earth, its composition, even the way it orbits our planet, all of these make our moon a fascinating subject of study. Before we delve into the most widely accepted theory, remember this: our moon is unique and its story is a thrilling one. Imagine a time about 4.5 billion years ago, a colossal event took place, an event that resulted in the creation of our moon. Let's delve into a theory that sounds like a plot straight out of a science fiction novel: the giant impact hypothesis. This hypothesis suggests that the moon was born out of a cataclysmic collision between the early Earth and a Mars-sized body named Theia. But how did this happen? Picture this: Theia, at high speed, smashes into the young Earth, a celestial body teeming with molten rock. The impact was so intense that it caused a large part of the Earth's outer layer and Theia to vaporize and be ejected into space. This cloud of vaporized rock and dust began to orbit around the Earth, and over time it started to cool and coalesce, eventually forming our moon. This theory is not just a wild guess, it's backed by several pieces of evidence. The similarities between the Earth's and the Moon's isotopic compositions, for example, strongly suggest their common origin. Moreover, the Moon's lack of iron, which is abundant in Earth's core, indicates that the Moon was formed primarily from the Earth's crust, not its core. Computer simulations of this event also support the giant impact hypothesis. These simulations show that the conditions and aftermath of such a collision would indeed create an Earth-Moon system with characteristics very similar to what we observe today. So, it appears that our beautiful moon is a child of violence, born out of a massive celestial collision. It's a testament to the dynamic and often violent nature of the universe. A serene silver orb in our night sky, the moon serves as a silent reminder of the chaos from which it was born. So, the moon we see today is a result of a catastrophic collision billions of years ago. Now that we know how our moon formed, what exactly is it made of? Just like Earth, the moon also has layers: a crust, a mantle, and a core, each with its unique composition. The moon's crust, its outer shell, is covered in a layer of lunar soil known as regolith. It's a mix of fine dust, tiny glass beads, and larger pieces of rock, created by billions of years of meteorite impacts. This crust is thicker on the far side of the moon, reaching depths of up to 44 miles compared to the near side, which averages about 31 miles. Beneath the crust lies the moon's mantle, extending down nearly 700 miles. It's composed primarily of minerals like olivine and pyroxene, which are rich in iron and magnesium. And unlike Earth's mantle, the moon's mantle doesn't experience plate tectonics or volcanic activity, resulting in a more uniform composition. At its center, there's the moon's core, a small and partially molten region. It's believed to be largely composed of iron, but it's much smaller relative to the moon's size, making up only about 2% of its mass. In comparison, Earth's core makes up about 1/3 of our planet's mass. So, how did we come to know about the moon's composition? Well, much of this knowledge comes from the moon rock samples brought back by the Apollo missions. These rocks told us that the moon's crust is largely composed of a type of rock called basalt, formed from cooling lava. They also revealed a surprising fact that the moon and the Earth share a remarkably similar isotopic composition. This finding provided strong support for the giant impact hypothesis that we discussed earlier. As it turns out, our moon isn't just a pretty face, it's a complex celestial body with its unique composition. Ever wondered why we only see one side of the moon from Earth? It's a fascinating result of a process called tidal locking. Tidal locking is a gravitational interaction where the moon's rotation period matches its orbital period around the Earth. This means that the same side of the moon, the near side, is always facing us. But how did this happen, you ask? Well, it's a tale as old as time, quite literally. In the early days of the moon's life, it spun much faster than it does today, but the gravitational pull from Earth created a bulge on the moon's surface. This bulge acted like a brake, gradually slowing down the moon's rotation until it became locked, with one side perpetually facing Earth. It's much like a spinning top that slows down and finally comes to a rest. But while we're always seeing the same side of the moon, its appearance changes throughout the month. This brings us to the phases of the moon, another captivating aspect of our celestial neighbor. The moon doesn't have any light of its own. What we see is sunlight reflected off its surface. As the moon orbits around the Earth, different parts of its surface are illuminated by the sun, resulting in the various phases. At new moon, the side of the moon facing us receives no direct sunlight, so we can't see it from Earth. As days pass, we see more and more of the illuminated part, leading to the waxing phases. At full moon, the side facing us is fully illuminated. After this, the lit portion we can see starts to decrease, marking the waning phases. This cycle of phases from new moon to full moon and back again takes about 29.5 days. It's a cycle as predictable as the rising and setting of the sun, and it's been happening for billions of years. Our moon's dance with Earth has resulted in this special relationship where we only see its one face. Such is the magic and mystery of our solitary lunar companion. Our moon is more than just a celestial body that lights up the night sky. It is a vital part of our planetary system, a companion to Earth in our journey through the cosmos, and a catalyst of curiosity and exploration. Let's delve into the significance of the moon to our home planet. The moon's gravitational pull plays a pivotal role in creating the ocean tides we experience on Earth. As the moon orbits our planet, its gravity tugs on Earth's water, causing the rise and fall of the ocean's surface, a phenomenon we know as tides. Without the moon, our planet would have a much more subdued tidal system, significantly altering the marine ecosystems we know today. Another fascinating role of the moon is its part in eclipses. Solar and lunar eclipses are cosmic events that occur when the sun, Earth, and moon align. Without the moon's perfect position and size relative to Earth and the sun, these awe-inspiring occurrences would not be part of our earthly experience. Moreover, the moon helps stabilize Earth's tilt. Our planet's axial tilt, which gives us our seasons, is kept stable by the moon's gravitational pull. Without the moon, Earth's tilt could vary dramatically, leading to severe climatic changes. Beyond its scientific significance, the moon has profoundly impacted human culture. It has inspired countless works of art, music, and folklore. It has served as the muse of poets and the guide of sailors. Its phases have been used to mark time, and its surface has been the destination of human exploration. Indeed, the moon's influence extends beyond its gravitational pull. It has sparked our curiosity, driven our technological advancements, and fueled our desire to venture into the unknown. From the Apollo missions that left the first human footprints on its surface, to the ongoing research and exploration, the moon continues to captivate and challenge us. Our journey to understanding the moon is far from over. It continues to captivate us, inviting us to learn more about its mysteries. As we continue to gaze upon it in the night sky, we are reminded of the vastness of the universe, our place within it, and the endless possibilities that lie ahead.